Hello, everyone. I literally just did this entire lecture. I made a whole 1 hour lecture and didn't have the microphone on. So now I'm doing it again so that you can hear me, because obviously that's what's the point. And so anyway, this is our lecture on solar radiation management, a form of geoengineering that has been proposed to offset some of the warming from climate change. And so we brought this up last class, so now we're gonna dive into it. I hope that this lecture is as informative as being in person in class with me, but I will say I miss you all terribly and feel like I'm really bad at talking to myself. And I'm also making my partner sit in the same room as me, so I'm actually talking to another human being. My dog is sleeping through lecture also, so there's that. Anyway, the image on the title slide here is, you may recognize, it's Edward Munch's Scream painting, where the sort of Scream face is the inspiration behind the Scream mask in the Scream horror movies. But what we're particularly interested in this painting is the color of the sky. The color of the sky is that color because there are little particulates in the sky that are reflecting and refracting some of the sunlight that's reaching the Earth, so it's creating this orangey glow. And these aerosols or particulates in the atmosphere are what we're going to focus on when we talk about solar radiation management and how we might be able to cool the temperature of the Earth down to offset some of the warming from climate change. So before we get to that, we have to review the radiation budget, which I know I've reviewed 100 million times in class and I've drawn on the board and da-da-da-da-da, but it can't hurt to go through it one more time. So I don't have my Coke Zero, but I do have my Crystal Light. So the radiation budget there are two sides of the equation. There is the incoming radiation from the sun, the solar radiation, which comes in the form of three wavelengths. Who remembers what they are? They are ultraviolet radiation, visible radiation, and what we call near infrared or short infrared radiation. A portion of that incoming radiation is reflected back to space. It never makes it into the Earth system, so to speak. And how much of that radiation is reflected? Does anybody remember? It's 30%. Good. And what reflects that radiation? This is where I would ask you in class, what reflects that radiation? And then you would, of course, tell me the correct answers because you are such a wonderful, smart group of kids. You would say snow and ice, desert, sand, the brightness over deserts, and clouds. Okay, so that's incoming radiation. Outgoing radiation, which we call long wave, or thermal, or terrestrial, or infrared. It's mostly infrared radiation. Is very different than the incoming radiation. So the outgoing radiation, the infrared radiation, gets emitted from the surface of the planet, makes it up into the atmosphere, where it is intercepted by tiny gas molecules known as greenhouse gases. And greenhouse gases absorb that infrared radiation, right? This is just a review. Absorb that infrared radiation, re-emit that infrared radiation in all directions, but because most of them are close to the surface, most of that infrared radiation comes back down to the surface of the Earth, and this process is known as the greenhouse effect. So when we talk about solar radiation management geoengineering, we are not dealing with the terrestrial radiation, the thermal radiation side of the equation. We're only dealing with the incoming shortwave radiation from the sun. So only this side of the equation, right over here. So the goal here is that if we intentionally change the Earth's albedo, and I know you all remember what albedo means. It's the reflectivity of the Earth 30%, right? The Earth's albedo is 30%, 0.3. If we intentionally change the albedo, change how much the Earth reflects, then we could theoretically reflect more heat back out into space and intercept some sunlight before it reaches the Earth through like basically a literal shade or mirror or putting something in between to reflect some of that sunlight. And we would need to increase the albedo, we would need to increase the amount of sunlight that we're reflecting by 2%, so from 30 to 32%, right, to roughly half the effect, the warming effect, that would result from a doubling of the amount of carbon dioxide in the atmosphere. So if we double how much carbon dioxide gas is in the atmosphere, the warming that results from that, we offset that by increasing the albedo by 2%. That's the idea behind solar radiation management techniques of geoengineering. So what are some of those techniques? Well, the first one, and the one we're going to spend most of this lecture on, is using stratospheric aerosols. Okay, and I'm going to talk about that quite a bit. Another technique is to brighten the clouds over the ocean, marine cloud brightening. A third is perhaps enhancing the sulfur cycle of the ocean, painting all the roofs white, putting reflective sheeting over the world's deserts, dumping a bunch of reflective trash into the oceans, putting literal space mirrors between the Earth and the Sun, or space sunglasses through like a diffraction lens, or perhaps just blowing up a side of the moon and putting a bunch of moon dust in between the Earth and the Sun to reflect some of that radiation. So we're going to start with talking about stratospheric aerosols. So stratospheric aerosols are tiny particulates that are emitted into the layer of the atmosphere that we call the stratosphere. So this image here is a cross-section of the atmosphere. You can see the layer closest to the surface we call the troposphere, clearly distinguished from, delineated from, the stratosphere, which is the layer above the troposphere. So it's not at the surface, it's the layer above the layer at the surface. Okay, oops. And when we look at these stratospheric aerosols, we're going to use an important natural phenomenon as an analogy. So volcanoes emit aerosols, they emit these particulates. I know we've talked about aerosols a bit in class, and I'll have a brief review of them in a second. They emit these aerosols, which can affect the climate. Okay, so we can use volcanoes as a really nice analogy to how this geoengineering technique might work if we were to actually do it. So volcanic eruptions produce a bunch of gas and a bunch of aerosols. Okay, particles suspended in air. So let's do a brief review of what aerosols are. I know I did this in class, in one of our last classes together. But just to review, we group the aerosols into sort of 4 broad categories. We have industrial aerosols, which are aerosols that are emitted from industrial activities like driving cars, factories, that sort of thing. These are mostly sulfate aerosols. They're very bright, they're reflective. When combined with water, they produce smog, which I think we're all very familiar with. So that's industrial aerosols. We also have sea salt aerosols, which are literally the salt that is normally dissolved in ocean water. When waves break or when waves crest, tiny bits of salt get activated and suspended into the atmosphere. They kind of emerge from the water and get suspended in the atmosphere and then act as also sort of bright reflective aerosols over the oceans. And if you've ever been to the beach and you have the not Lake Michigan beach, the ocean beach, where because there's no salt in Lake Michigan, right? So if you've been to the ocean beach and it looks kind of hazy, that's the sea salt aerosols. We also have over the deserts and other drier areas where there's a lot of sand and those types of particles. We have desert sand, which we in the climate community call dust. So dust is an important aerosol as well. It gets activated. We see it in the satellites. There's a lot of dust orbiting the Earth at all times. That's being sort of suspended and activated from deserts, winds blowing over deserts. And then finally we have smoke, which is emitted from forest fires and wildfires and other crop burning fires. And this smoke is different than industrial emissions of aerosols in that it's typically darker. So it's made from organic and black carbons. It's not nearly as reflective. It is reflective, but it's not as reflective as, for example, industrial sulfate aerosols. It's more absorptive and has slightly different effects on the climate. So actually, let's talk about what those effects of aerosols are on the climate in more detail. So we have three kind of main effects that aerosols can have on the climate: the direct effect, the indirect effect, and the semi-direct effect. So the direct effect depicted here, in which we're going to focus most of this lecture on, is you put a bunch of aerosols into the atmosphere in between the sun coming down towards the Earth. They're bright, they reflect that sunlight, and they cool the surface of the planet. So they have a cooling effect. There's also the indirect effect, where you pump a bunch of aerosols up into the atmosphere and they get ingested into a cloud. And as they get ingested into a cloud, they increase how bright that particular cloud is. And of course, if you make a cloud brighter, you cool the surface. And so both the direct and the indirect effects have a cooling effect on the climate. They cool the climate down, actually. We also have the semi-direct effect. The semi-direct effect results from darker aerosols, which are generally emitted from fires. These aerosols have high black carbon concentrations. They're much more likely to absorb rather than reflect sunlight. And this absorption of sunlight can actually warm up the atmosphere, which would increase how stable the atmosphere, which prevents clouds and thunderstorms from forming. And so if you have less clouds, you have less thunderstorms, then you have a warmer surface. So the semi-direct effect actually has kind of a warming effect on the planet, whereas the direct and the indirect effect generally have a cooling effect on the climate. Okay, does anybody have any questions? This is where I would ask you, does anybody have any questions on this? But I will leave those questions in the discussion of that for the Slack when we have our group hangout in the Slack. Okay, so back to volcanoes. Volcanoes inject gas and aerosols into the atmosphere. These injections of gases, for example, cause a sort of minor, very minor, long-term warming, millions of years warming. But the aerosols have a relatively short-term cooling effect, the direct effect, and so very important study into how aerosols can cool the climate on a very large scale. The other thing about volcanoes is that they are tall. I mean, they're high up there, you know, typically. And so they emit aerosols into the stratosphere, which is what we're talking about here. We're talking about stratospheric aerosols. So if we're going to geoengineer the climate with stratospheric aerosols, we can use volcanic eruptions as an analogy for how this might work in the real world. So when volcanoes erupt, the aerosols enter the stratosphere. There's very little moisture in the stratosphere, so the aerosols are not removed by clouds and rain. They just kind of hang out there, and over many, many months and perhaps years, they eventually get large enough where they settle out and they fall out on their own. So they don't get rained out, they fall out on their own. So as I said, these aerosols have a short-term cooling effect on the climate, especially if they're in the stratosphere for months and years. They can have a pretty strong effect on the climate. So eruptions emit sulfur. That sulfur in the atmosphere combines with water to form tiny drops of sulfuric acid, H2SO4. These droplets form this haze that I'm talking about, this like layer of aerosols, which reflect sunlight back into space and cause cooling on the surface of the Earth. So this is an example of what that looks like. And this example in particular from the eruption of Mount Pinatubo in the Philippines is one that we're going to focus on in the next lecture because we have a lot of data. It's a very fairly recent eruption. We've had satellites, we've had weather monitoring and instruments. So we can say a lot about what happened as a result of Mount Pinatubo to the climate. But this is just an example of the sulfur cloud that was produced by the eruption of Pinatubo in 1991. So you can see that sulfur gets up into the stratosphere and then spreads out and really covers the whole planet over time. Eventually, the sulfuric acid droplets will become large enough that they'll fall back down to Earth, but this process could take months and years, and so this is why it's a good analogy for us to study as climate scientists. Again, also the location of where the eruption has occurred will affect the magnitude of the climate effects, and you'll see it's the difference between an eruption happening near the equator in the tropics or at the poles much further from the tropics. And this would also inform, if we're going to actually geoengineer with stratospheric aerosols, where do we put the aerosols for maximum effect? But more on this particular case, this Mount Pinatubo case, in the next lecture. So first, some questions, some answers. Do volcanoes emit more carbon dioxide than humans? The answer, of course, is absolutely not. Degassing volcanoes add between 0.13 and 0.44 gigatons of carbon dioxide to the atmosphere every year. Conversely, human activities in 2020 emitted about 35 gigatons of carbon dioxide, so quite a significant multiplier there between the two. And to put it in perspective, like a large eruption, the 1980 Mount St. Helens eruption emitted about 10 million tons of carbon dioxide in 9 hours. Humans, however, do this in about 2.5 hours. We can emit the same amount of carbon dioxide in just 2.5 hours. So volcanoes are not really a big contributor. At least the gases from volcanoes are not a really large contribution to climate warming. There is an exception if we look historically through Earth's past climate. Siberian traps, volcanoes in Siberia, for example, may have emitted between 13,000 and 43,000 gigatons of carbon dioxide over a period of like 1 million years, which caused a very gradual long-term warming. But this is very different than the acute warming we're seeing in the last 100, 150 years. If you're interested in like learning about the history of Earth's climate, I also teach a class, Earth's Changing Climate, which looks at we deal with stuff like this. We talk about things like this. So if that's something, you should take that class when we have in-person classes again. So that all said, that background, excuse me, sorry. This is my second time giving this lecture, so my voice is, of course, now hurting. So let's look at some case studies of some of the major volcanic eruptions in human history. And we're going to use 3 case studies. We're going to talk about 2 of them today, and then the third one, Pinatubo, we're going to talk about next week because, again, as I mentioned, there's a lot more details on Mount Pinatubo. So we're going to start with the eruption of Mount Tambora, and then we're going to talk about the eruption of Mount Laki, and then, again, next week is Mount Pinatubo. So let's start with Tambora. Tambora is a stratovolcano, a large stratospheric emitting volcano located in Indonesia. It's located right here on an island just to the east of Java, one of the most populated islands in the world. That's where Jakarta is, of course, very densely populated island. Tambora is a volcano that is formed and driven by the subduction of the Australian plate underneath the Eurasian plate. So subduction, you've got 2 plates. Try to do this backwards. You've got 2 plates. Subduction is one of those plates is going underneath the other. Okay, so that's subduction. As this plate slides under the other tectonic plate on their surface, it starts to melt. This magma, newly formed magma, then finds its way back up and forms a volcano at the intersection of the 2 plates, essentially, due to that subducting activity. These volcanoes tend to be really violent. They erupt pyroclastically. they emit a lot of ash and things all at once, like in a big explosion. So the eruption of Mount Tambora in 1815, the trigger for that, geologists have been unable to identify, but it was a massive, massive eruption, which had a few direct effects, not really climate-related per se. Produced about 100 cubic kilometers of material. You can see in comparison with some other major stratovolcanic eruptions like Pinatubo, which I keep mentioning, or Krakatoa, also a major volcano in the tropics, tropical Asia. Tambora produced like 10 times as much cubic kilometers of material than, for example, Pinatubo did. And we consider Pinatubo to be a massive volcanic eruption. So Tambora was a big one, real big one. The pyroclastic flows themselves alone killed 10,000 people, just from like the debris, the lava, the rocks, all that stuff. And the pyroclastic flows entering the ocean, right? We saw this, I don't know if any of you were watching the news when Hawaii was erupting a couple of years ago, and like the lava was like sliding into the ocean, forming new land. Well, these pyroclastic flows from Tambora were so enormous that they generated tsunamis, which some of were up to 13 feet high, which devastated some of the neighboring Indonesian islands. And the cloud of ash produced by Tambora and just in the sort of local vicinity of the eruption itself blocked out the sun and caused the temperatures to drop by 28 degrees Fahrenheit almost instantaneously. Within 20 miles of Tambora, the villages were covered in about 40 inches, so 3 to 4 feet of ash, and even up to 100 miles away, those villages were covered between 8, 10, up to a foot, for example, of ash, okay, of aerosols and particulates falling out of the sky. So massive, massive eruption. Even a small quantity of ash, as this quote says, even a small quantity of ash could devastate plants and wildlife. For example, one district that received about 1 1/4 inch of ash discovered that its crops were completely beaten down and covered by it. Dead fish floated on the surfaces of ponds, and scores of small birds lay dead on the ground. So ash is very devastating, just in a direct way, not thinking necessarily of the climate way, but just the ash itself, and how it can sort of pollute crops and wildlife. Of course, the volcano also emitted a lot of sulfur that when it got up into the atmosphere and the stratosphere became sulfuric acid, about 100 million tons of sulfuric acid. And I found this like painting here of the eruption of Mount Tambora, very idyllic looking painting, which I know if we were all having class together, we would have a fun laugh about it, because it's like this massive eruption, like deadly, biggest in the last however many years, and it's pictured like just like this sailboat here. It's just like chilling, like no big deal. Anyway, so the cloud of sulfuric acid that was emitted by Tambora circled Earth within 2 weeks, so it got all the way around the planet, covered the whole planet in ash in the stratosphere, and ultimately we think it caused a dramatic cooling of up to a degree of Celsius, 1 degree Celsius of cooling, which is about double what we think occurred as a result of, or what we observed occurred actually as a result of the eruption of Mount Pinatubo. So big eruption, massive effects on climate around the world. Something that we also need to talk about is that this eruption not only changed the temperature of the planet, induced this cooling, also the changes in heating and cooling in the stratosphere affected precipitation patterns around the globe. And so if we are going to geoengineer using solar radiation management techniques, using this stratospheric aerosol technique, we need to consider how the injection of these aerosols into the stratosphere could change more than just the temperature, could change the precipitation patterns, and whether this would be worse than just having climate change. And that's a debate that I don't know that anybody really necessarily has a good answer to, honestly, and doesn't really even have a good way to test. So, what happened as a result of the eruption of Tambora, climatically speaking? So I mentioned that it decreased global temperatures by between half a degree Celsius for many years following. Specifically in the following year, 1816, the eruption decreased the temperature so much that many people call that year the year without a summer. It was a very cold, rainy summer in the northern hemisphere, especially where most of our understanding of the climate effects come from. Since most people live in the northern hemisphere, I'm rambling. Anyway, it also destroyed crops worldwide, resulting in famines, epidemics, perhaps even a pandemic. For example, in June of 1816, there was frost reported in upstate New York and Maine, where a lot of farming and agriculture was happening at the time. Failed harvests in Britain and Ireland led to massive famine and typhus epidemics. As I mentioned, the change in precipitation patterns broke the monsoon cycle in Asia and South Asia, which triggered famine and a cholera epidemic in India. There were cold snaps throughout the summer and very rainy days, which ruined the rice paddies in China, which also caused widespread famine. And possibly as a result of these ruined rice paddy crops, farmers at the time increased production of poppies, which are used to make opium, and perhaps this was the beginning of an increased demand for opium products. There was also a massive cold snap in New England during this time, 1815, 1816, which caused a lot of farmers to actually migrate west with the death of these crops. And a lot of fledgling states at the time west of New England, or fledgling territories, hadn't quite yet become states. And so, for example, Indiana became a state in 1816, Illinois became a state in 1818, possibly as a result of, or at least partially influenced by, the change in climate due to the eruption of Mount Tambora. There was a boom and then a bust of grain production, which ultimately people think led to the Panic of 1819. Of course, the cost of food increased dramatically during this time of famine. The price of oats, for example, increased, which made it very expensive to feed horses, and horses at the time were the major mode of transportation. And so it's possible that because of this, around this time in 1817, the bicycle was invented in Germany as a response to sort of alternative ways of transportation besides the horse, if it was becoming sort of prohibitively expensive to feed them. Here's a map showing the summertime temperature anomaly for the European continent during the summer of 1816. So the blues and the purples indicate cooler temperatures than normal. Okay, normal, weather minus climate, right? We've talked about this. So you can see that over much of Europe, temperatures were between 2-3 degrees below normal, averaged over the whole summer. And this is 2 to 3 degrees Celsius, so like, what is that, 4, 5, 6 degrees Fahrenheit. Averaged over the whole summer, that's a pretty significant cooling. It was also during this summer where Mary Shelley wrote of the weather and the days and the way she was spending her time. At first, we spent our pleasant hours on the lake or wandering on its shores, but it proved a wet, ungenial summer, and incessant rain often confined us for days to the house. And so while confined in her house, looking out at gloomy, cool, cold, wet, gross summer weather, Mary Shelley wrote the novel Frankenstein, possibly influenced by the climate at the time. And Frankenstein, of course, was later published in 1818. So I'll just finish this discussion of Tambora with some quotes from around that time. So one by Lord Byron: "I had a dream which was not all a dream. The bright sun was extinguished, and the stars did wander darkling in the eternal space. rayless and pathless, and the icy earth swung blind and blackening in the moonless air. And then another quote here, people rush from falling houses in their thousands. It is worse than the work of thieves. Bricks crack, walls fall. In an instant, my house is gone. My child catches my coat and cries out. I am running in the muddy road, then back to rescue my money and grains from the ruins. What else to do? My loved ones must eat. So, tying this back to that title slide, that Edvard Munch painting, the ash, the stratospheric ash, right, all that stuff in the stratosphere, is really good at scattering light, but specifically it scatters shorter wavelengths, so blue and violets, which allows more red and orange wavelengths to come through. So the sunsets around this time were quite vivid in these years following Tambora and also Krakatoa and also Pinatubo. And so it's possible that these really vivid sunsets inspired artists like Edvard Munch and J.M.W. Turner to make these paintings where the sunsets are very golden, golden and reddish. There's a lot of art from this time depicting this type of scene and perhaps inspired by the actual weather outside due to this volcanic eruption. So just to review, the eruption of Tambora was the largest and deadliest eruption of the 19th century, not the 20th century. That's wrong. So don't listen to that. Resulted in about 10,000 direct deaths and probably millions of indirect deaths from famine, from disease, etc. The eruption did, in fact, cool the climate, caused major effects like spread of cholera, increased opium production, perhaps the invention of the bicycle, these paintings, the Panic of 1819. And so Tambora is really informative when we think about the ways in which stratospheric aerosols will impact climate. We look at what happened during Tambora, where it produced a 1 degree C cooling, which is about what we're hoping to achieve here. Another example is the eruption of Mount Laki, which is a totally different type of volcano in a totally different geographical part of the world. So Laki is in Iceland. It's a vent eruption, so not like a big explosion, pyroclastic. It's more just like slow over time. And it began in June of 1783, so much earlier than Tambora. So just where is Laki? Laki is in Iceland up here, very close to the North Pole, close to the Arctic Circle, right? Distinctly different geographical location than Tambora, which is down here in Indonesia, right? Laki is a vent volcano, so vent eruption, so it's basically being emitted from these fissures, kind of like how the volcano in Hawaii has been erupting or was erupting several years ago. You see the lava flows down, forming new land, emptying out into the ocean, etc. So this eruption, instead of happening in a matter of days or hours like Tambora, happened over 8 months. So a very long duration event. And it did emit about the same amount of sulfuric acid as Tambora. About 180 to 120 million tons or 100 cubic kilometers of material. Okay, so similar, but different temporal scales and different geographies. So directly Laki, and this is different from like aerosol direct effects. This is just like the actual direct effect of the volcanic eruption. So the direct effect, basically it mainly produced some minor plumes and lava fountains, very fast pulses of lava flows, fast as perhaps the flow of the Ohio River. I can't pronounce this guy's name, but here's a quote on how fast the lava was flowing. So the flood of fire flowed with the speed of a great swollen river in meltwater on a spring day. Great cliffs and slabs of rock were swept along, tumbling about like large whales swimming, red hot and glowing. Okay, it seems that my camera froze or something. Cool. Well, I'm going to pause this. Oh my god. What happened? Literally, the recording froze. I'm gonna die. This is awful. No, like I can't stop it, so I have to just.